you have to write the voltage across the inductor VL equal to L into di by dt. The voltage across the inductor equal to L into di by dt. This one formula you have to. We can also write VL equal to d by, this is VL equal to L into di by dt. VL equal to L into di by dt. Can also write d by dt of Li. What is Li, friends? Psi equal to Li. This is also equal to d psi by dt. The voltage across the inductor is also equal to d psi by dt. Once you know the voltage across the inductor, then how to calculate current to the inductor? How to calculate current to the inductor? Very important observations. The current through the inductor equal to current through the inductor. How to write the inductor? Once you know the voltage across the inductor, I am calculating current through the inductor. Then VL equal to L into di by dt. From this, di equal to VL by L into dt. To get the current, integrate both sides. Integral di equal to, that is 1 by L into integral VL into dt. How to take minus infinity to t. Why you are taking this minus infinity? Because it is a energy storage element. If it is energy storage element, let's assume that already there is some initial current in the inductor. Then if you integrate this, how you can write, friends? This I equal to, I am writing like this, 1 by L, this 1 by L, integral minus infinity to 0, V dt or VL dt, that is the voltage across the inductor, plus 1 by L, integral 0 to t, VL dt. Then what this indicates? This current I equal to, this is the initial current in the inductor. If initial current in the inductor is not given, you have to take this is 0. IL of 0 into 1 by L integral 0 to t VL dt. This is also very important for this. If initial current in the inductor is given, you have to take this one, where IL of 0 equal to initial current in the inductor. Initial current in inductor. The initial current in the inductor equal to IL of 0. If initial current in the inductor is 0, then you have to write what is the voltage across the inductor. If initial current in inductor is 0, if initial current in inductor is 0, if initial current in the inductor is 0, then how you can write current through the inductor? I equal to, how to write current through the inductor equal to, initial current in the inductor is 0 plus integral 0 to t VL 1 by L dt. This is equal to 1 by L integral 0 to t VL dt. Let if it is VL equal to V, simply write 1 by L integral 0 to t V dt. If voltage across the inductor equal to V, then you have to write this. This is the expression for current through the inductor. How to write the expression for current through the inductor and how to write the expression for voltage across the inductor. But here, how to give very important observation during solving of the problems. These observations are. See, for example, this is a note 1. During solving of the problem, based on these models, based on this observation, already questions are there in GATE and ESE. For example, we know that voltage across inductor equal to VL equal to L into di by dt. Voltage across inductor equal to L into di by dt. If current is parabola, if different current shapes are given, if current is parabola, then what is the voltage, friends? Then what is the voltage waveform? What type of waveform we can get? L into d by dt of current is parabola. Na? What is the differentiation of parabola we can get? What is the differentiation of parabola we can get? Can anybody? What is the differentiation of parabola we can get the ramp? That means if current is excitation, if it is a parabola, then you have to take the voltage is ramp signal. If current is ramp, then can anybody tell what is the voltage across the inductor? L into d by dt of differentiation of ramp. What the differentiation of ramp will use? Step function. Differentiation of ramp will use the step function. If current is step steps, then what is the voltage across the inductor waveform? voltage across the inductor waveform. Differentiation of step, what it gives? Impulse. Differentiation of step gives the impulse. For example, if current is triangular wave, if current is triangular wave, current is triangular wave. If current is triangular wave, what is the voltage across the inductor space? L into d by dt of triangular wave. Triangular wave. Then differentiation of triangular is square wave. Differentiation of triangular wave is square. If current is sine wave, what is the voltage across the inductor? If current is sine wave, what is the voltage across the inductor? Which waveform, sir? Yes, it is a cosine wave. Differentiation of sine will use the cos. Like this you have to identify. Sometimes it will give exactly opposite. If you write exactly opposite, note 2 I am writing. What the current through the inductor, friends? What is the formula for current through inductor? Current through inductor. The current through inductor, I equal to 1 by L integral V dt or VL dt. How to write? V dt or 1 by L integral VL dt. Now, if voltage is impulse, if voltage is impulse, then what are the currents, friends? 1 by L integral differentiation of impulse. Sorry, integration of impulse. What integration of impulse will give? Differentiation of step gives impulse, means integration of impulse gives step. Reverse process. This gives the step. If voltage is step, then what the current? 1 by L integration of step. What the integration of step gives? Ramp. Differentiation of ramp is step, then integration of step is ramp. If voltage is ramp, then what are the currents, friends? The current I equal to 1 by L integral ramp. Integrating, we can get parabola. Differentiation of parabola ramp, integration of ramp is. Then if voltage is square wave, friends, square. If voltage is square wave, then what is the current we can get? 1 by L is a square wave. No? Differentiation of square wave gives triangular wave. So integration of square wave, not differentiation, sorry. Integration of square wave gives triangular wave. Differentiation of triangular wave gives square. Like this, during solving of the problems, this observation. This exactly reverse. This is differentiation. If you integrate this, we can get this one. This is differentiation of this. You integrate this, we can get. Integrate this, we can get this. Integrate this, we can get. If you integrate this, you can get this. Exactly. Students, we know that inductor is a energy storage element. It stores energy in the form of magnetic field. Stored energy in the form of magnetic field. But one observation you have to remember. See, for example, note I'm giving one more note. This is inductance. The current is entering. This is I. This is plus. This is minus. Then in this case, L storing the energy. L storing the energy. L storing the energy. If current is flowing like this is the inductor. This is the inductance. If current direction is like this, if the current direction is like this is plus, this is minus, this is plus, then current is leaving at positive, then we can say that L releasing the energy. L releasing the energy. L releasing the energy. And one more point to remember, L storing the energy, na? VL equal to L into di by dt. If L storing the energy, di by dt is positive. The slope is positive. The rate of change of current is positive. If L releasing the energy, this is the positive slope, friends. This is the positive slope. If L releasing the energy, what is the di by dt? This VL equal to L into di by dt. Then di by dt is negative. That is falling slope. Releasing the energy is a falling slope. Storing the energy, rising slope. All these observations important. This is one direction. This is opposite direction. L releasing the energy. But one point you have to remember here, friends. The property of inductor is like this. See, for example, initially inductor stores the energy. If the current is like this is very important. There is a main difference is there in inductor and capacitor in storing and releasing. Like this is the current direction. This is plus, this is minus. Then we can say that it is a storing. Then Once inductor completely store the energy, the property of inductor is it forcibly reverses its polarity. This becomes negative, this becomes positive. It reverses its polarity after complete storing. After complete storing, or if source is disconnected, reversing polarity. After reversing the polarity, then release the energy. After reversing the polarity, then release the energy. This is a property space. Then release the energy. Releasing the energy. This is happening. That is the property of inductor is once it completely stores the energy or source is disconnected. The property of inductor is once it completely stores the energy, once it completely stores the energy, or excitation is disconnected, or if excitation is disconnected, inductor forcibly reverses its polarity. Inductor reverse its polarity. Very important observation, sir. During releasing, first reverse the polarity, then release the energy. During releasing the energy, first reverse the polarity, then release the energy. But capacitor is not like that. If you take capacitor, later on also I will explain. Let's assume that this is plus, this is minus. Let the capacitor is plus minus, it is the storing. Like this, it is storing the energy. Then, how to reverse the polarity? In capacitor, this is storing. Then capacitor release the energy. Second step is release the energy. Directly is not reverses polarity. Then capacitor release the energy. Let it is releasing the energy. Let assume that if the capacitor is, what do you mean by capacitor releasing the energy? Transfer of the charge from positive plate to negative plate. Then release the energy. This is release the energy. Second step is release the energy. Release the energy means transfer of charge from positive plate to negative plate. Once it is transferred, then it becomes negative, this becomes positive, then reverse the polarity. So why this difference? The reason is it stores the energy in the form of electric field, it stores the energy in the form of magnetic field. This is the property of magnetic field. This is the property of electric field. Here, reverse the polarity, release the energy. Release the energy, then reverse the polarity. Then reverse the, these two observations also you have to. That's why in releasing and reversing the polarity, there is a difference in the inductor and here releasing the energy means what is the meaning? Transfer of energy from positive plate to negative. Then negative plate becomes positive plate becomes negative. Transfer of energy from positive plate to negative plate. Next. And one more observation. Slide I'm adding. Sorry. Just 10 minutes. I'm adding the slides. One more observation that you have to concentrate. Students, we know that V equal to L into di by dt. That is V equal to voltage across the inductor. What is the observation here, friends? At t equal to 0, means initially. T equal to 0 means starting, initially. You substitute t equal to 0, then what is the voltage across the inductor? Infinity. Voltage is infinity means open circuit or short circuit, friends. Voltage across the inductor is infinity. Voltage infinity means open circuit or short circuit? Open circuit. At t equal to 0, inductor acts as a open circuit. Open circuit means is current is exist? No. There is no current. That is initially, suddenly there is no current to the inductor. That's the reason why inductor cannot allow the sudden change of currents. Inductor, why voltage infinity means current is 0. At t equal to 0, I am explaining. Inductor cannot, in detail about this, later on we'll see in the transient also, but up to now you remember this is a property of inductor. Inductor cannot allow the sudden change of currents. Inductor cannot allow the sudden change of current because initially inductor acts as. Therefore, initially Inductor acts as an open circuit. Inductor acts as a open circuit. Inductor acts as a open circuit. Next, at t equal to infinity, t equal to infinity means final steady state. Finally, substitute t equal to infinity here. What the voltage across the inductor? See, voltage across the inductor 0 means open circuit or short circuit? Short circuit. Voltage 0 means short circuit. Voltage 0 means short circuit. Therefore, finally, inductor acts as a short circuit. Finally, inductor acts as a short circuit. That is at steady state condition. Finally, inductor acts as a short circuit. Acts as a short circuit. That is at steady state. Inductor acts as a short circuit. Then we know that V equal to L into di by dt. V equal to L into di by dt. From this, what is all these are the observations? V by di by dt. Then what are the units? The units I told already. One more unit I am giving. This dt goes to numerator. This dt goes to numerator. That is volt to dash second by amperes. Volt to dash second per amperes. The dt goes to numerator. That is volt dash second per ampere. Or the another unit is Henry. This is the units of inductance. The units of inductance. And we know that inductors store the energy in the form of magnetic field. How to calculate stored energy? The fourth observation is stored energy in inductor. This is very important formula that I am going to get. Stored energy in inductor. This is very important. 5-star gunshot formula. How to calculate the stored energy in inductor? We know that inductor stores the energy in the form of magnetic field. Inductor stores the energy. Stores the energy in the form of magnetic field. Form of magnetic field. Yeah, this is also very important points. Don't forget this. Initially, inductor acts as an open circuit. Finally, it acts as a short circuit. Because of initially it is an open circuit, it cannot allow the sudden change of store the energy in the form of magnetic field. Then, in order to calculate what is the energy stored by the inductor, first I am calculating the instantaneous power. Instantaneous power. Then, how to calculate the instantaneous power, friends? The instantaneous power P equal to V into I. What is V? L into di by dt. That is L into di by dt. This is into I. Yeah, this is the instantaneous power that equal to Li into di by dt. Li into di by dt. Yeah, this is the instantaneous power. Once you know the instantaneous power, how to get the energy? Then what is the energy stored by inductor? Energy stored by inductor. The energy stored by inductor equal to E equal to RW. Any notation you have to use. Integral P dt. Here you have to use either capital letters or small letters. No problem. I'm following the capital letters. Then you have to use, that is the L into di by dt into I. That is L into Li into di by dt. Li into di by dt. Then I'm calculating energy stored by inductor. The energy stored by inductor here W equal to integral Li into di by dt into dt. This dt cancel. Then what the energy stored by inductor? The energy stored by inductor equal to L is constant, I into di. You integrate I with respect to di, friends. Integrate I with respect to di. What you can get, friends? I square by 2, sir. I square by 2. Therefore, what is the energy stored by inductor? The energy stored by inductor. The energy stored by inductor E equal to half Li square. Half Li square. So this is the energy stored by I. Very important 5-star gunshot form. It's a calculation of how much energy is stored by the that is called the concept, right? Yes, but you can also write this formula. What is psi equal to Li? Psi equal to Li. Shall I write I equal to psi by L? Where psi is the flux linkage friends. Then energy stored by inductor, one more formula is half into L. I am writing psi by L. Psi by L whole square. Then what you can get, friends? Psi square by 2L. That is one more formula for energy stored by the inductor. Psi equal to Li. That I am writing I equal to psi by L. psi square by L square, LL cancel, then we are getting the psi square by 2L. These are the different concepts of inductance or inductor.
Sure.
Any doubt? Is it clear, sir? If you have any doubt, please raise the question, then I will. Any doubts, friends? It's okay. Yes. Then what are the practical examples of inductor, students? What are the practical examples of inductor? Just like resistors, I told already what are the practical examples of resistors, like heater, iron box, incandescent lamp. Like there's so many examples I give. Mission field windings. There's so many examples I give. Like that, what are the practical examples of inductor? The practical examples of inductor is one is choke coil. Choke coil is one of the example for inductor. It is having the inductive nature. Even transformer is also having the inductance, inductive nature. Transformer windings, transformer. And AC mission windings also inductive nature. It is also having resistance, no doubt at all, but it is also having AC mission windings also having it. Even you take some passive filters also having the inductive nature. Passive filters. All these are the practical examples of the which having the inductive nature. We know that L filter, C filter. No? What is the purpose of using L filter? What is the purpose of using L filter? To reduce ripple in load current. So this one of the inductor filter. Inductor filter is the having inductive nature to reduce ripple in load current. To reduce ripple in load current. Reduce ripple in load current. We are using inductor filter. But point to remember, friends, practical inductor having resistance and capacitance also. Resistance and capacitance also. Resistance and capacitance also. No doubt at all. Any practical inductor you have to take. This is inductor. Practical inductor is represented with, along with inductor, there is some resistance, series resistance. How to use resistance. Then practical inductor is having some inductance and it is also having the resistance. Then what is the time constant? The time constant equal to L by R. The time constant equal to, in detail about this in the explanation of transient concepts, in analysis of RL circuit, RC circuit, RLC circuit, in DC analysis and AC analysis, later I will explain. But this one formula you have to remember. This is the time constant. But you have a doubt here, sir. Resistance okay, but how the inductors are having the capacitance? Students, we know that inductor is nothing but a, you take one core. On the core, we can place one term. Again, on this term, we have to place some insulation. On the term, you have to place the one insulation. Again, we place the one more term. Like this, we can manufacture. Like this, we can construct the inductor. That means in inductor, this is one term, this is another term. In between, there is an insulation. This is one conductor, this is one conductor. In between, there is an insulation. Two conductors are separated by some dielectric material. It acts as a capacitance. That means that is called turn to turn capacitance. That is in capacitance, there in inductor, there exists a capacitance between turn to turn. Okay, this is called self-capacitance of coil or distribution capacitance of coil. Okay, that is called, actually it's negligible, no doubt at all. But practically, every coil is having some inductance, every coil is having some resistance and capacitance also. But actually that is negligible. If you take this is the coil, inductive coil, then this is called a turn to turn capacitance. In some exact analysis, you have to consider this turn to turn capacitance. So this is the seed. This is called distribution capacitance. This is called distribution capacitance or self-capacitance of coil or self-capacitance of coil. Every coil is having some capacitance. This is called distribution capacitance or self-capacitance of coil. Practically, this distribution capacitance or self-capacitance of coil, it is calculated, practically it is calculated by using Q meter, by using quality factor meter. The distribution capacitance or self-capacitance of coil is calculated by using you have to conduct an experiment using Q meter, then you have to calculate the self-inductance or, you have to calculate the distribution capacitance or self-capacitance of a coil. And one more point how to remember, friends. One more important point. We know that if the core is like this, it is a solenoid coil. If the length of the coil, if the length of the core is L, that is the air gap length is the L. This is L. How to take this is the coil. We know that how to write the inductance. L equal to N square mu A by L. This formula all of you L. N square mu A by L. But if the coils are like this, if this type of coil it is given, there is a coaxial shape. If it is a coaxial coil, that the coil is like this, it is given. Okay, this type of coil it is given. The shape of the coil is like this. This is the shape of the coil. It is also inductive coil. Okay, this is placed like this. Just where am I? For this type of shape, how to consider the length of the coil? Can anybody? For this type of shape, how to consider the length of the coil? The length of the coil is equal to circumference. Is it correct? The length of the coil equal to circumference. In this case, inductance equal to L equal to N square mu A by L. But what is L here, friends? Where L equal to 2 pi. Now take the total circumference of the coil is nothing but a L equal to 2. Actually, in the explanation of resistance also, note for resistance, R equal to rho L by A. Rho L by A. If it is a circular or if it is a straight conductor, you have to take this form. If the resistor, if the resistor is this shape, friends, this is called coaxial shape. Just like coaxial cable, it's like this. If it is a resist, I'm writing for resistance formula also. I think electrical students, you know this formula, but AC students, you don't know. In cables, you studied about this. This is the inner radius, and this is the outer radius. Inner radius and outer radius. Then for this case, how to calculate the resistance? This is capital R is the outer radius, small r is the inner radius. Then resistance equal to, in this case, the resistance equal to 1 by 2 pi L, 1 by 2 pi L, ln of capital R by small. This formulas also you have to remember. Here, resistance is inversely proportional to length. Very important. Generally, resistance is directly proportional to length. For this coaxial shape, it is given. Then resistance equal to, this is equal to 1 by 2 pi L ln of R by this resistance. This resistance is measured. Mainly in cables, you have to calculate the insulation resistance. Then you have to calculate this 1 by 2 pi into ln of R by R. Okay, this is about the detailed discussion of the inductance. The property of inductors are very important. Inductance cannot allow the sudden change of current. Initially, inductor acts as a open circuit. Finally, inductor acts as a short circuit. Finally, inductor acts as a short circuit. Then inductor cannot allow the sudden change. Inductor store the energy in the form of magnetic field. Inductor store the energy in the form of magnetic field. All these points you have to consider. Friends, any doubt up to now? I started what is the inductor, inductance that I given. Then final conclusion point that you have to write with respect to inductor. Then finally, the inductor is a also linear element. Inductor is a linear. Therefore, the final conclusion point is, and final conclusion points, friends. Therefore, inductor is a linear. It is a linear element. Bilateral, both the direction it offers the same impedance. Bilateral, same reactance it offers. Bilateral, time invariant. It's not a time variant. Time invariant. Linear, bilateral, time invariant, passive. Is a passive element. Passive element. This is the linear, bilateral, time invariant, passive element. Passive element. This is the final conclusion point with respect to it. Here I'm giving one small question, friends. Can anybody answer? So, for example, a practical time constant for a practical inductor, for a practical inductor, for a practical inductor, for a practical inductor, if the number of turns in the coil is double, if the number of turns in the coil is double, if the number of turns in the coil is double, if number of turns in the coil is double, coil is double. Then its time constant is, what is its time constant? Then its time constant is, time constant is. Can anybody? Then its time constant is. How many times it becomes? The time constant is 2 times or 3 times or 4 times or remains same. Try this. Answer this. So I'm giving practice one. Tomorrow I will ask this question. Answer. For a practical inductor, if number of turns in the coil is double, the coils are double, turns in the coil is double, then it's time. If the number of turns in the coils are double, then it's a time constant. Yes, friend, this is the about a detailed discussion of inductance. Then how to start the capacitance. When I start this, it will not complete. Better to continue tomorrow. In tomorrow class, I will complete this capacitor concept. Then we have to see some practice questions with respect to inductor and capacitance. How to see some practice questions with respect to inductor and capacitor. All these practice questions that I have solved. Then with this, elements, RLC elements will complete. That is the basic elements in the circuit theory. Resistor, inductor, and capacitor concepts will be complete. And after that, we will see the types of elements. Then KCL, KVL, model analysis. Students, any doubt? Okay, thank you. If you don't have any doubt, then I'm ending the session. I will share this PPT. Please go through this once again. Thank you, students.